The dot product is a very important operation between vectors that we use in physics. For example, the concept of work, which is a transfer of energy, which we will see later in the semester, is one of the fundamental properties that is most utilized throughout branches of physics. So the dot products between vectors, we're going to look at two different approaches to calculate it, and it really depends on how the problem is stated or what we're given to work with. The first one we will look at is going to be the geometrical approach, which is probably also the one that we will consider to be the easiest. If any of you have seen dot products before, which I hope you have seen in this kind of a review, then this is probably the approach you have seen, or at least remember or recognize. So the geometrical definition of a dot product the name comes from the fact that we're using quantities associated with the geometry of the vectors to calculate it. So for example, the dot product between two vectors A and B is read as A dot B, hence the name of the dot product. So the dot product name comes from the symbol that we use to represent it in math. The dot product can be calculated or defined as the length of vector A. Now, the length of a vector is a geometrical quantity we can associate with a drawing or sketch of a vector. We take that and multiply by the length of vector B, and then we take those two, or the product of those two, and multiply by cosine of the angle between them. So the angle between those two vectors is also a geometrical property of like a sketch, if you look at it that way. So we call this the geometrical definition. The length of A times the length of B times cosine of the angle between them, that will give you the dot product. The dot product is a scalar, or just a number associated with potential units. So there's no directions associated to that, which makes it a lot easier than the next one we're going to see, which is the cross product. Alright, so let's take an example here. I hope this is relatively straightforward. You don't need to memorize the equations, you just need to, I prefer you understand the conceptual meaning behind it, which we will look at in a little bit, and then we can always look up the equation. Okay, so let's take two vectors, or consider two vectors, have a length of 5, length of 3, and the angle between them is 15 degrees. And then let's calculate the dot product. We simply take the equation and then it's plug and chug. Plug in the two lengths and cosine of 15. Type it out of your calculator. Make sure your calculator is set to degrees when we input the angle in degrees. And we do that, we get 14. So that's the dot product between those two vectors. We may at this point have absolutely no clue what that means, other than it's a number 14. So I did not provide any units with A and B, therefore this here will also just be unitless. But if the A and B, for example, had been in meters, it would be 14 meters squared. Okay, we notice there's no reference to a direction or anything like that, because it's not a vector anymore. The dot product is not a vector, it's a simple number. Okay, example number 2 is, I think, rather important for the next way to define the dot product, and that is to find the dot product between unit vectors. So unit vectors are characterized by the fact that they have a length of 1, and then the unit vectors that we have in what we call the Cartesian coordinate system, we have a unit vector along x, we have a unit vector along y, and we have a unit vector along c. In this example, we will consider unit vectors x and y. Those two unit vectors are perpendicular to each other, and therefore the angle between them is 90 degrees. So let's try and find the dot product between two unit vectors ex and ex. So that's the same vector. And what we find is that it's the magnitude multiplied together, 1 times 1. Since it's the same vector, they're pointing in the same direction, the angle between them will be 0. Cosine of 0 is 1. So we get that the dot product is just equal to 1. On the other hand, if we take the dot product between unit vector x and unit vector y, they both have the length of 1, so that's 1 times 1. But now the angle between is 90 degrees. Cosine 90 degrees is 0. And we get that the dot product is 0. And this is a fundamental property of dot products. The dot product between vectors that are perpendicular are always going to give you 0. And we will see in the next section with the interpretation why that is. So for the interpretation, I'm making a sketch here. So I'm sketching a vector A just laying horizontally, and then a vector B offset by some angle. So we have an angle theta between those two. If you look at the definition we just had above, that the dot product is the two magnitudes times cosine of the angle, I can kind of separate these things. I can say, okay, let's consider the length of B times cosine of the angle. What does that mean? Well, a length of a vector times cosine, if you go back to trigonometry and we think about these in terms of right angle triangle, then if we look at the vector B to be the hypotenuse in a right angle triangle, then the length of vector B times cosine angle is going to be the projection down to the adjacent side of the angle. And that's what I sketched right here with this curly brackets. So this is a projection. This is, so we can call B, or the length of B times cosine of theta, we can call that the projection of vector B onto vector A. Now this is not the dot product itself, but it's part of the dot product. The remaining part of the dot product is to take that projection and multiply it by the length of A. But remember, if we take a length and we kind of multiply it by a projection, that's a scaling of some number, right? We can take a number 2, we can multiply number to another number, we're scaling the, if you wish, we're getting a new number, right? That's really what this is. This is a projection times a number, which is just the length of A. We can also look at, if you take the projection of B and we consider that as a component vector, then it's the projection vector onto A, and then the length of A will be scaling it as well. So this is kind of a measure of how much overlap there is between vector A and vector B. So that is the interpretation of the dot product. A larger dot product, a greater value of the dot product, tells you there's a greater overlap between two vectors. So if you take two vectors that are perpendicular, what is the overlap? Well, this vector here, for example, has 0 projection onto this one. So no projection, no overlap, therefore the dot product is 0. On the other hand, if we have two vectors that are parallel, we're going to have a maximum overlap. And that's simply the two lengths multiplied together. So that is the the interpretation of the dot product. All right, let's go down to the second way we can define this dot product, and that's the analytic definition. And when it's said as a definition, it's actually a definition in the sense that we can derive it from the first definition. So maybe we shouldn't really call it definition, but maybe just call it an analytic approach. However, it's often written as a definition because it gives us another tool on how to calculate the dot product. And reality is you could also define it this way and derive the first definition we had. So in this case, if you're going to not look at the geometrical properties of vectors, but instead of the analytic properties. So the analytic properties is to consider the components, these numbers associated with the vector. So remember, from the vectors and the unit vectors, we can write any vectors as a scaling of unit vectors and then adding them together. So a vector A in 2 dimensions, for example, can be written as a number times a unit vector in the x direction, and it just tells us how far in the x, on which direction does the x component go. And similarly, we can take a y component, do the same thing, and we can take our x, a y component, and depending on the length they have, we can create any vector in our 2-dimensional space. So we're writing our vector A as a component in the x direction times a unit vector, and it's the same thing for the y direction. We take our second vector B and do exactly the same thing. So now our vectors are represented by ax, ay, bx, and by, which are the components of the vector. They're no longer represented by the length and the angle between them. Now, we could figure that out if we wanted to, but for now, we don't want to. So the dot product is an operation in this linear vector space, and they follow similar rules as they do in number space, as we're so familiar with. So we just simply take our vector A, write it in component form with the unit vectors, and we dot it with the vector B. So that is the equation we have right here. Okay. We have not done anything other but just inserting the expressions for vector A and B. The next thing is we can now distribute through the dot product. And this is one of the operations that we are allowed to do. If you want to learn more about those operations, that's the class of linear algebra. So we distribute through, it's simply taking our first term in the brackets with the A vector multiplied by the first term in the second parentheses and so forth. So we distribute through here, so we get AX times unit vector EX multiplied, or I shouldn't say multiplied, by dotted with the first term of the B vector and so forth. So we distribute through all the terms here. So we're getting these 4 terms now. These are all dot products. What we have to keep in mind is that the dot product is an operation between vectors, not an operation between numbers. And the components we have are just numbers. So the numbers are not affected by the dot product. So we can move those numbers, AX, BX, AY, BY, we can move those outside the dot product. So that's what we have done in this step right here. We're simply taking all the scalars of these numbers and grouping them together, and what is left is a dot product between vectors. More specifically, dot products between unit vectors. But guess what? We just did that up in example 2. So now we take our values that we have from example 2 and we insert here. For example, the dot product between unit vector x and unit vector x is equal to 1. So that gives us a 1. The dot product between unit vector x and unit vector y give us a 0, and so forth. So now we just have numbers only. AX BX times 1, AX BY times 0, and so forth. And we can write our final results as the dot product between A and B are the x components multiplied together plus the y components multiplied together. So that's a relatively simple rule. So it might have looked uglier up here, but that's kind of like showing how we get there. And even though we say, I don't need that, I don't want to see that proof, I don't care, there is a greater understanding of the material and subject if we can understand how we obtain our results. So what we have now, we have 2 approaches we can calculate the dot product through. If the problem states here are the length and angle, then we choose method 1. If the problem states here are the components, then we should choose option 2. Okay, so here are a couple of examples for you guys to try and work through. And here's some important observations. And these are things we can, as we've gone through this here, maybe some of them already said, but just summarize the ones we already said. Number 1, the importance of projection. It's only the component of one vector onto the other that matters. So if you have 2 vectors that are perpendicular, there's no projection, it doesn't matter. If you take them at an angle, it's only the component that is along the other vector that matters. The one that's perpendicular does not matter. We do not need any information about that component. We only need information about the component along the second vector. The magnitude of a vector, based on the way we wrote the dot product in the second form, in component form or analytic form, we can see if we take a dot product between a vector and itself, we're getting the square of the length of that vector. And that's a really important property if you take the next level of physics, but also in math. The third and last important observation we're going to make is that if you're going to find the angle between 2 vectors, these 2 vectors do not have to be forming a right angle triangle, which means trigonometry is in most cases not going to work right off the bat. However, you can absolutely find components of these two vectors, find the angle that each vector is making, and then do addition / subtraction to find the final vector. It's a lot of work. It is in fact easier in most cases to use the dot product to actually calculate the angle, because we can rearrange the first definition we had on how to calculate the dot product. We can rearrange that so we can actually find the angle between the two vectors if we do know their dot product. Okay, so the rest of the notes here are simply some boxes to kind of test your understanding of it. And again, keep in mind that these notes here are nothing more than just some brief notes. Joining office hours, recitations, reading textbooks, working through problems in your textbook is another way, or should be in addition to these notes here. And then you can test your understanding with the boxes. And if the notes are sufficient for you to go through the boxes, then that's great, of course.